Thanks for the introduction. Yeah, I'm Macoretta, PhD student, just finished PhD last week at the University of Pisa, and I'll show you a work that is part of my PhD thesis, that is part that deals with the mechanical behavior of Inconel 718 manufactured by using high productivity selective laser melting high productivity rate selective laser melting process parameters. And this is a work that is done in collaboration between our research group at the University of Pisa and the research group at the Norwegian Technology University. The outline of the presentation. We see the development of two sets of productivity-oriented process parameters. We'll see the effect that they have on the surface roughness of the specimen produced and on the inner porosity. We'll see our experimental investigation on the static and cyclic mechanical properties. We'll see the fractalographic investigation after the fatigue test, and we'll see an attempt to rationalize the behavior fatigue data that we have within the framework of the area method proposed by Professor Murakami. So, the material. Material, Inconel 718, the standard powder size distribution that is used for selective laser melting process. Selective laser melting process was carried out at the university, the laboratory of selective laser melting of the University of Pisa, where we have a Renishaw printer, RENM 500E, that is a new introduced printer that has the capability of reaching 500 watts of power, and so it allows us to increase a bit the productivity and the power that we input in the process. All the specimens were built in vertical direction. Here you can see the specimen on the plate, and on the right the standard dimensional one. Our specimen, this is the dimension for the fatigue specimen, the tensile one are similar, just with the normal adjustments. The surface condition investigated is only the S-built surface condition because we want to understand the effect on surface roughness. About the treatment, it was tested both the S-built and standard aged material for Inconel 718. And about the test, static test, tensile test, Picard-ness measurements, and high cycle fatigue test on cylindrical plate specimen on a stress ratio with a repeated load, so 0.05. The test frequency was about 115 Hz, and the test temperature only room temperature for this testing. This is about the development of the process parameters. I used an analytical modeling of the selective laser melting process that is a model that exploits the Rosenthal solution, so it's an approximate solution, but it can provide an analytical prediction of the thermal field that we have in the material. Here I just provide you an overview. We'll explain it better in a dedicated paper that here we have no time to be a lot with. But this model that works with a pointed source moving along a straight line, steady state, semi-infinite solid, so it's something that works properly for the etching part of the specimen, not for the contour part. It's something in the boundary. And what we obtained the prediction of the thermal field produced by the laser scan, and so the Merkur dimension in terms of the radius of the Merkur, and in terms of the elongation of the Merkur. And so the aspect ratio, that is the ratio between the length and the radius of the Merkur. And obtaining the dimension of the Merkur, we can obtain a lot of information about the occurrence of electrofusion phenomena. So when the Merkur is too small for having a good fusion of the material, and our humping phenomena that are phenomena linked to the elevated aspect ratio Merkur. When the Merkur is too elongated, some instabilities can arise, and instabilities in the end lead to porosity in the material. We tested 5 sets of selective laser melting process parameters. The values suggested by the manufacturer of the printer, so Renishaw, that here is called baseline, and it's almost in line with the standard that we can see in the market. And where we have an aspect ratio of the Merkur of about 5 using the approach that I showed before. But we tested also other 3 process parameter set. One is A0, that is the one where that we found in the literature with the highest aspect ratio, that has an aspect ratio of about 8, and 2 parameters that we developed within this framework. There are 2 parameters where A1 has the same aspect ratio of A0 but has a higher productivity, and A2 has an increase in the aspect ratio. This here in black you can see this is the region where we have electrofusion. So the 2 process parameters were designed to have the same margin of the electrofusion of electrofusion. It's about 20% margin in the dimension of the mercury compared to the one that could lead to electrofusion in this approximation that I showed before. If we consider a simplified job with 20 specimens that are square section bar 10 millimeters per 10 millimeters per 100 millimeters printed in vertical direction, just to have an example to evaluate the productivity of the process, we can see that we pass from 13 hours for the baseline case. Here in this case we neglect the time of the recoder and other time that are fixed in this approach. While we can reduce, with the A0 we reach a reduction by 32%. When we pass to A1 and A2 process parameters, we almost halve the build time. So we can really increase the build rate and the productivity of the process. But what is the price? The price is that we introduce in the material some defects. Here we see the porosity on the left part for you. You see the baseline condition where almost there are no pores. This is a metallographic section in longitudinal direction, vertical direction of the specimen, just to show you a better view about the distribution of the pores compared to metallographic section carried out in the transversal direction, in the direction perpendicular to the building direction. We can see that in the A01 we have almost no porosity in the middle, but some pores arising on the contour part of the specimen. I forgot that. We use the same process parameters both for the hatching and for the contour parts. So we have a increasing the roughness in the contour compared to what we can do if we adopt the parameters focused on reducing the roughness. But our focus was to investigate the effect of the defects, inner and surface defect for the materials. So we adopted the same process parameters for both etching and contour part. We can see that for A1 and A2 we have an increase in the size of the pores. We have regions that are most full dense, but sometimes we have larger pores, really larger pores. These pores arising from the stability of the mercury, from the fact that we have mercury with a high aspect ratio, and in some cases these stabilities create region with higher pores. In fact, if we see the material density, we see that with all the process parameters, we are above the 99.5 threshold that is what is usually considered the full dense material. But we see that passing from baseline to A2, we have a decrease in material density, and we see if we analyze the pore circularity, that is what can distinguish pores that arise from gas entrapped bubbles from pores that arise from electrofusion or hampering defect that in the end lead to local electrofusion phenomena. We see that pore circularity decreases moving from baseline to A0, A1, and A2 process parameters. That is the expression of the stability of the mercury I was saying before. If we look at the surface of the specimen, here we can see metallographic section carried out in the longitudinal direction. So here you can see the mercury and the build direction is on the horizontal line, and you can see the baseline, the A0, A1, and A2. You can see that the surface of the specimen has a smooth waviness in the baseline case, while this waviness becomes more pronunciated and with more steeper valleys, passing from A0 to A1 and finish to A2 condition, where we have really steep valleys with that at their root has region with high stress concentration. If we see the measurement of the roughness except from these profiles but image elaboration, we can see that the roughness is increasing monotonically from baseline to A2 process parameters. As the process was speed up and the mercury are more elongated, the process is more unstable, and so we see this increase in the roughness on the surface, both in the average and in the total rate of the roughness. And the other interesting aspect that we observed is the variation in the pitch of the roughness. While on the baseline case we see this waviness that is average, more frequent value in the pitch between two consecutive valleys depth of 418 microns. When we move to A1, A0, A1, but in particular A2 parameters, we see that the more frequent values is lower. It's about 240 microns. But we continue to observe higher pitches. So we have a superposition of a short pitch, that is something that arises from just here you have to consider that the layer thickness is 60 microns, 60 microns. So here you have something that is 4 times the layer thickness, while you have here that is 6 times the layer thickness. So the difference is that when you move from baseline to ATU process parameters, you have an addition of short pitch and a long pitch, and the long pitch is between the steeper valleys. You can see also here you have these 2 steeper valleys, but you have also this valley in the middle. That when we investigate the stress, the effect on the stress distribution, we can see also effects of stress shadowing because of this pitch distribution. Okay, show you better after in the finite model simulation. If we pass to the static test in the S-bit conditions, so tensile test, we see that passing from baseline to A0, A1, A2 produces more or less an increase in the yield strength and also in the ultimate strength when the necking phase is reached, but a strong decrease in the elongation and fracture. That is something that is due to the inner porosity of the material. So you can see that in terms of ultimate stress, it's almost constant, but in terms of elongation and fracture, it's really decreasing. And also, if we pass to the aged material, we see the same effect. The yield strength and ultimate stress are almost unaffected, but the elongation and fracture is strongly reduced. And then this elongation and fracture reduction produces also a reduction in the ultimate strength because it's not reached the same point. Say. If we investigate what happened in terms of weaker hardness, here you can see the axis of the image is a path from the center towards the outer part of the specimen, measured on transverse direction with polished surfaces. You can see that, the hardness is almost constant, and the variation in parameters produces an effect that is almost the same of the scatter that we have in the weaker hardness measurements, and also both in the S-bit condition and in the aged condition. Only in the S-bit condition we can see a small effect in terms of an increase in the hardness in the outer part in the ATU and A1 process parameters, probably because of a higher thermal gradient due to a higher velocity of the process. If we go to the fatigue test, so I'll show you directly all the SN cubes of that we tested. You can see that in comparing to this huge increase in the surface roughness and porosity, the fatigue strength is not reduced so much. If we deal with if we compare the baseline and the ATU process parameters that are the two extreme in terms of productivity, we see that ATU produces only a 5% reduction in terms of fatigue at 1 million cycles here. The fatigue test was limited only in the part between 10 to 5 to 10 to 6 seconds to failure. And then, due to these results, we decided only to age the baseline and the ATU process parameter that are the most promising one. And we see that also in the aged condition, where we expected a strong reduction in fatigue strength due to the increase in the ultimate strength of the material and in the end in the not sensitivity of the material, we can see that the fatigue strength reduction is only 4%. It's really low. If we go to fractographic analysis, in terms of the S-based material, all the fatigue cracks had their onset on the surface, where we have for the baseline some small defects due to roughness, with A1 and A2 some bigger defects, but in any case present on the surface. Also, if we pass to scanning and thermal investigation, we can see that in the baseline case we have a small onset with a smooth propagation, while if we pass to ATU, we see that we have a more rough surface and we have also secondary cracks, and so ratcheting because of multiple crack incision sites. And the other interesting aspect is the presence of non-propagating cracks. These are photographic inspection of specimen after the fatigue testing. We see that in the baseline case we have some small discontinuities on the roughness on the external profile of the specimen that are really sporadic. In ATU case, we have a lot of these steep valleys, and at the root of the valleys we can observe these non-propagating cracks. These that they have a length of 20 to 30 microns, let's say. And based on this idea, we try to explain the fatigue behavior of this material. First of all, producing finite element model simulation that takes into account the profile of the specimen. So from the metallographic investigation, it was extracted the profile of the specimen with some smoothing, obviously, to avoid the powder that is on the surface, and it was created for each portion of the specimen a dedicated CAD model, and then the finite element simulation of a specimen with an axisymmetric model, only with the material considered only isotropic and elastic in this first approximation. And yeah, what we obtained is that here we can see the longitudinal stress of the baseline condition and of ATU condition. And for both the two materials, the stress concentration, the theoretical stress concentration is not one. Also in the baseline case, we have a theoretical stress concentration. But if we compare the two conditions, the stress concentration is almost double. But when we see the fatigue result, the fatigue result is not so much effective. So we tried to investigate within the framework developed by Professor Murakami, in particular in view of the presence of non-propagating cracks. So what we can say that the fatigue limit is something that is governed by the threshold condition for non-propagation of crack emanating from surface valleys through. So within this approach, we consider the equivalent area based on the height of the roughness and of the pitch between two consecutive roughness valleys. The pitch was evaluated from the finite element simulation, so we consider the pitch only between the more steep valleys, avoiding the smoother ones that are in the middle. And what we obtained that we found the hardness constant from the baseline conditions. So these one are equal due to the method, but the prediction was really good on the baseline condition or the edge condition. And when we go to see what the method predicts for the fatigue reduction for the other parameters, we see that the prediction with this approach are strongly in line with the experimental results. And so just to finish, what we saw that with a material that is like an additive manufacturing material that is already full of defects, adding some other defects leads to a saturation effect. Adding other defects doesn't produce a linear decrease in fatigue strength. We have something that, yes, is a fatigue strength, but it has only an increase in the strength, in the, let's say, in how the valley is steep, but the width as built surface, we have already valleys that are the governing factor for the fatigue of the specimen. And so we have a huge increase in the surface roughness, but only a very low decrease in the fatigue strength. Thanks for the attention.
Thank you. Is there any questions from the audience? Just one quick question. There's time. Yes, please.
I suppose that you showed that the roughness of the surface increased about 120%, isn't it? At the conclusions.
Yeah.
But it has only influence of 5% of worse fatigue.
Yeah, it's something that surprised me.
That.
Yeah, but if you go with this approach, this is the standard formula. Now we introduce the correction in this hardness parameter just to fit exactly the baseline case. This produces a variation, not 120. But after you introduce this correction for matching this, you have this one that is matched perfectly. And also here you see that, the variation, these are the variation between the predicted and the experimental one. You see that it's not exactly perfect, but if you introduce the Murakami approach on the roughness, the hardness, and also the increase of the roughness, because of the fact that they are within this term, their increase has only a slight increase, the effect on the fatigue strength that is in line with what we observed. In particular in the SB case, because in the aged case, I'm sorry, because on the SB we have high ductility of the material, so high toughness. In the aged case, the material has really reduced toughness, and so it's something that so surprised us.
Okay. Thank you again.